So we were talking about expected values, right? Averages, linearity. So just continuing right where we left off. I owe you a proof of linearity. I don't like being in debt, so let's start by proving linearity and then do some more examples. We started on some examples last time, but continue just seeing why is linearity so useful. Linearity of expectation. Okay, so start with the proof. This is kind of my own proof of linearity. I call it, well, I don't know what I call it, but I like this proof better than the ones that usually one sees. Basically, remember last time we wrote down a list of numbers and we averaged them in two different ways. One is the naive way, just add them up and divide by how many numbers there are. And then the other way was we grouped the same number together, right? Group them together and take the weighted average. It's the same thing. That's basically the proof of linearity. It just doesn't seem that way until you think hard enough about it. So I want to explain that point of view to you rather than doing tedious calculations. So here's what we're trying to do. We're looking at the sum of two random variables. Let's call it t for total. T equals x plus y. And our goal is to show that the expected value of t is the expected value of x plus the expected value of y. Show e of t equals e of x plus e of y, which, as I said last time, is pretty obvious if x and y are independent, but not at all obvious, at least to most people, if x and y are dependent. And this is always true as long as these expectations exist. Now, you could have random variables where the expectation doesn't exist because the sum diverges or something like that. But as long as these numbers actually exist, this is always true, even if they're dependent. Okay? So here's kind of like the first attempt. What if we just tried to directly prove this? It looks kind of straightforward, and you can say, well, sums are linear and so on. It should be kind of easy. Let's just try to do this brute force from the definition. What would we have to do? Well, we'd have to write down the definition of e of t, definition of e of x, definition of e of y, and see is it the same. So here's e of t. E of t is the sum over t. Right now I'm assuming that they're discrete. I'm going to prove it in the discrete case. We haven't dealt much yet with continuous random variables. We'll be coming to that soon. But the proof is analogous in the continuous case anyway. So right now we're working with discrete random variables. That means we have a PMF, and the expected value is the sum of t times the PMF. So remember this from last time. We're just taking a weighted average of possible value. Little t is a possible value of capital T, and that's the PMF, so it's just a weighted average. So I'll put equals with a question mark, because this is what we want to see whether this is true, e of x plus e of y. So for e of x, we would take the sum of x, sum over x of x times the PMF of x, and then similarly for y, y times the PMF of y. Okay? I'm assuming they're all discrete random variables, so we can work with the PMFs. So there's a question mark here. So now we need some kind of a strategy. How do we deal with this? Well, I guess there's two strategies I can think of just off the top of my head. One would be try to mess around with the right-hand side and show that it equals this. The other would be try to mess around with this and show that we can split it up like that. Okay, let's consider both strategies. Strategy one, try to combine these into this. Well, I have this. This is a sum over x. This is a sum over y. How do we combine a sum over x and a sum over y? It's just like two sums, right? I don't really see how to put them together. So let's consider the alternative approach. Take this thing. Now, how can we break this apart? Well, this is a little bit more promising. I mean, it's not obvious, like, how is t going to split up into an x and a y? But we can try to play around with this p of t equals t. In particular, we could take p of t equals t, and our most important strategy is conditioning, right? So what do we wish we knew? Well, it would be useful to know x or to know y, so let's condition on x. So I could write this as the sum over little x, probability that t equals t, given x equals little x times the probability that x equals little x. Now, capital T is x plus y. And if we know x is little x, we can plug in little x there. If x and y are independent, then we could simplify this. And it'll be kind of similar to when we proved algebraically that the sum of binomials, independent binomials with the same p is binomial. We did the algebraic proof of that. It reduced to the Vandermonde thing. So it would look kind of like that if x and y are independent, and we could eventually probably work it out to this. Well, that's if x and y are independent, okay? But I didn't say x and y are independent. So if they're dependent, then you're just kind of stuck with this given x equals x forever. Right? You can plug in x equals little x, but there's still going to be a y here, and then it's y given x, and then you're stuck. So, okay, so that doesn't work. Let's do this from another point of view, but just by looking at Pebble World over here. So I'm just going to draw a simple picture. Let's just suppose x has 4 possible values, and I just assume that I've arranged my sample space such that they're kind of arranged by column. Remember, a random variable is a mapping from the sample space. The sample space is the set of all pebbles to the real line. So suppose I've arranged my pebbles. I'm just for simplicity and to have a picture, I'm assuming x can only take on these 4 possible values. But the same idea would work for any discrete random variable. Let's just have a picture I can draw easily. So suppose that there are 4 pebbles. Each of these pebbles gets mapped to x equals 0. So that means we have this random experiment. If the outcome is one of these 4 pebbles, then we say x equals 0. If the outcome is one of these 2 pebbles, we say x equals 1. And maybe these 3 pebbles go to x equals 2, and this 1 pebble goes to x equals 3, okay? So that's what a random variable is. Any discrete random variable conceptually looks something like this. Now, let's just make an observation about how we can do our summation. E of x, we defined it to be the sum over all values x of x times the PMF. That was the definition. But notice that we could do this a different way instead. That is to sum not over values of the random variable, but sum over all pebbles. So this is the space capital S, and I'm thinking of each individual pebble as a lowercase s. X of s, remember x is a function, so x of s makes sense, times the mass of the pebble, which we just write as p of s. Remember, we have these different pebbles whose total mass equals 1. P of s is the mass of pebble s. Okay? So notice this is the same thing. And that's obvious once you've stared at it enough to understand what we're doing here. Because it's the same thing as doing the average in 2 different ways like we did last time. This one is the grouped one. This one is the ungrouped. So what we're doing with this sum over all pebbles is we're just taking, each pebble is assigned a certain value, and we're just averaging them all together, right? It's a very obvious thing to do, just take the average. Of course, it's a weighted average because some of the pebbles have higher probability, possibly. On the other hand, as in this picture, we could first group together all the pebbles that get assigned x equals 0, group together the ones that assign, x equals 1, and so on, group all these together. You can imagine these 4 pebbles with x equals 0 kind of clump them together, glue them together into a super pebble. The super pebble has mass equal to the sum of these masses, right? Glue these 2 together, glue these 3 together. This one's already 1 pebble. So you could group them together. That's exactly what this is saying to do, right? Because we group them all together and then give it a larger mass, right, if it's a super pebble. Okay? So that's just immediate just by thinking of how we could do averages by grouping together terms that have the same value, right? Okay. So that's true for any random variable x. Now let's prove linearity in the discrete case. And the continuous case is basically the same, but we'll talk more about continuous later. Okay, so what do we have to do? Well, let's just use this same identity for t instead of for x. So we could say, well, what's the probability? Not the probability, what's the expected value of t? That's this definition got us stuck. Let's use this way to write it as a sum over all pebbles. So it's the sum over all S of x plus y of S P of S. By definition of what does it mean to add two functions? Well, it just means you compute both functions and add them. That's just the definition of adding functions. So that's really just the same thing as x of S plus y of S times P of S. And now just distribute, this times this plus this times this, and break the sum. Now everything is summed over the same S, whereas here it was annoying because we had a sum over x, sum over y. Here, everything is a sum over pebbles. So now we just write it as two sums. That's just the sum of x of S, P of S, plus the sum of y of S, P of S. But that's, according to this identity again, that's just E of x plus E of y. And so that's the end of the proof. So it's almost immediate once you see that you can write expected value as a sum over pebbles rather than in this original form. Okay, well now I have a clear conscience about linearity. There was one other fact about linearity, which was that you can multiply by constants. So I'll just say similarly, do the exact same thing, except it's even easier in this case if we multiply it by a constant. E of c times x equals c times e of x, if c is a constant. That's the other part of linearity. And to see that, just use the same thing again. It's just multiply both sides by c, take out the c. So this one is more intuitive, I think, because it just says, the expected value of 2 times x is twice the expected value of x. So we use that a lot. But by the way, actually, this one, I think this seems pretty simple, right? If you multiply all the numbers by 3, you multiply by the average by 3. It's pretty natural. But this also helps explain some of the intuition for why is this true even if x and y are dependent. Because remember, it's very useful to look at extreme cases. So here's an extreme case of dependence. What if x equals y? That's as dependent as they can get, right? They're the same thing. Now, if that's true, then e of x plus y, since it's the same thing, it's e of 2x equals 2e of x, which is in fact the same thing as e of x plus e of y. Okay, so that's not a proof of linearity, but that's just checking that in that extreme form of dependence, it's true. And in the case of independence, then it's pretty intuitive that this should be true. And so we've covered both extremes, and the proof covers everything in between. All right, so that's linearity. So let's do some more examples of how we would use that. Here's another one of our famous distributions. So we're going to have a whole by the end of the semester, we're going to have a list of 13 or 14 extremely important distributions in statistics. So you might ask, what makes a distribution important, right? Because there are infinitely many distributions we could write down. We just choose whatever PMF we want, or create any CDF we want, and then that's some distribution. And why are we being so undemocratic about it? And we keep talking about binomials and geometrics when we could be talking, everyone could make up their own. Well, the reason is that the most important ones all have nice, useful stories behind them. So we saw the story of the binomial, the story of the geometric, the story of the hypergeometric, and there's just a few more of those that we're going to need soon for discrete. There are only a couple more discrete ones we need for the entire semester, and then there's going to be a bunch of continuous ones that we'll get to later. But as far as discrete ones, I think there's only 2 more that we need. So we'll do one today and one on Wednesday, and then we're done with all of the famous discrete distributions that we need in this course. Okay? So one of them is called the negative binomial. Don't be fooled by the name. The name negative binomial usually might make you think that you take a binomial and then make it negative. like multiply by -1 or something. But negative binomial is actually not non-negative, and it's not a binomial. So it's kind of a misnomer, but that's standard terminology. Actually, what the negative binomial is a generalization of the geometric distribution. So negative binomial, it has two parameters, R and P. And the story is that, like remember with the geometric, we were doing Bernoulli trials over and over and over again until getting success for the first time, and then we counted the number of failures. This is the extension to the case where you want R successes. Okay, so it's the number of so again we have independent Bernoulli P trials, like with the geometric, and we want to know number of failures before the rth success. So keep trying and trying and trying until you have R successes, and then count the number of failures. That would be called a negative binomial. And let's find the PMF. Let's find the expected value. Okay? So what's the PMF? Well, to find the PMF, basically we just need to draw a little picture for ourselves and then think about the picture. So the picture is just a sequence. Well, let's write 1 for success and 0 for failure. So maybe it looks like this: 1, 0, 0, 0, 1, 0, 0. I'm just making something up right now. And let's choose a value of R. Let's say R equals 5. 0, 0, 0, 0, 1, 0, 0, 1. Okay, I just made up a sequence that has 5 1s in it and however many zeros I just felt like writing. Okay? Now, I claim that if we stare at this binary sequence long enough, we can just write down the PMF without having to do any further work. So that's good. Don't want to do a lot of work. Just want to write down the PMF. So what's the PMF? Well, I say you just stare at this, so maybe we all need to stare at this a bit. I'm saying that R equals 5, just for the sake of example, because I drew 5 1s. R equals 5. And well, I guess I have to do some work counting the zeros. How many zeros were there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 11 zeros? So we want the probability that x equals n, let's say, if x is negative binomial. X equals n would mean that there are 11 failures, right? So since there are 11 ones, n equals 11 in this example. Okay, and p is whatever it is. We don't have to worry about p right now. All right, now notice one very important, simple but important fact about this sequence. It ends in a 1, right? That's the rth success right there. Okay? That could not have been a 0, right? Because if that was a 0, that would either mean we had not yet achieved our rth success, or we'd achieved it earlier, and then why were we continuing? Okay? So one thing I know for sure is that when you stop this, it's going to be with a success, right? Now, let's consider the rest of this stuff. If I permute these zeros and ones, would that still be valid? Yeah. It didn't matter, right? I mean, I can change these however I want. So amongst here, there are 4 successes, meaning we have not yet gotten our 5th success. So permute these however you want. It's not going to change things. It's not going to change the probability. It's not going to change whether it's valid or not. So amongst these earlier terms, we know that there are 4 successes and 11 failures, right? But those could be in any order. And those are the only possibilities, right? We need to have the rth success, and then the earlier stuff, we already know how many zeros, how many ones it could be, but they could be in any order. Okay, now we can immediately write down the PMF. The PMF is going to be, first of all, the probability of this particular sequence. This particular sequence had R successes, and each success has probability P, and there are n failures, so it's 1 minus p to the n. That's the probability of this particular sequence that I wrote down. Then we have to multiply by how many possible ways are there to rearrange it. This 1 has to stay here, but the ones before it, the terms before it, could be in any order. So all we have to do is select the locations of the zeros, or equivalently select the locations of the ones. So we can do, how many terms are there before? Well, it's n plus r minus 1, just everything except the last one. And then we just have to choose where the successes are. There's r minus 1 successes, so we could do r minus 1. We could also do choose n. Remember, it's the same thing. So this is for n equals 0, 1, 2, and so on. So that's the PMF. The reason it has the name negative binomial is just that in combinatorics, this kind of series is closely related to what you would get if you did the binomial theorem. You know, the binomial theorem is a plus b to a positive power. If you expand out a plus b to a negative power, you get something closely related to this. So it's like a negative power in the binomial theorem. But that's just the etymology of the term, and we don't need to worry about that. For our purposes, what we care about is the story, and we care about the PMF, and then we care about, you know, what can we do with this? Well, the next obvious thing to do is compute the mean, right? So let's find E of x. Okay, so we have the PMF. So in principle, we can compute the mean just by taking the sum of n times this, summed over all n. And that looks pretty nasty. So let's try to think of a better way to do it. Better way to do this is to say, well, first of all, if r is 1, remember, think of simple and extreme cases. If r equals 1, then it's just a geometric, and we computed last time in 2 different ways that a geometric p has expected value q over p, okay? So we know the case r equals 1 already. Now let's think, okay, well, a slightly harder case, r equals 2. So we are waiting and waiting and waiting until we have 2 successes. But a natural way to view that would be, first you wait for your first success, and then you wait for the second success, right? And in general, if you want to wait for r successes, you can think of that as first wait for the first success, then wait for the second and the third and the fourth. So therefore, we can interpret this as, I'm going to rewrite x as x1 plus blah, blah, blah plus xr, where xj is the number of failures x1 is the number of failures before the first success. x2 is the number of failures between the first success and the second success, and so on. So xj is number of failures between j minus first and j successes. For x1, I'm just interpreting it as the number of failures, you know, to start with before the first success. So number of failures between the j minus first and jth success. Then we already know the distribution of xj. Xj is just geometric p. Now, in this case, the xj's are even independent, but we don't even need that for this calculation. So they're independent because, you know, if you just imagine we have independent trials, so you wait a certain amount of time for the first success, and then I'm talking about the additional, from that point onward, starting at that point, how many more, and keep going like that. So they are independent, but we don't actually care. By linearity, this is just E of x1 plus blah, 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 plus E of xr. Therefore, that's equal to rq over p. So that's another calculation you could do in your head, because just in your head you just think, well, wait for the first success, and then the additional for the second, and the additional for the third. Each one of those is geometric p, so each one of those is q over p, and there's r of them, so it's rq over p. I just took q over p, and I multiplied by r. So it's very, very easy if you think of it that way, and very, very nasty if you don't think of it that way. Okay, so that's the negative binomial. And I want to just mention that you do have to be careful about conventions, both for the geometric and the negative binomial. Some books start the geometric at 1, which would mean you're counting the success, and we are starting it at, both conventions are common, starting it at 0 or starting at 1. They're both very common in the literature. For example, Ross starts his geometrics at 1, and de Groot starts his geometrics at 0. And we're starting our geometrics at 0, so we're following more like the de Groot convention, which again is very common as well, but both conventions are common. For the geometric, I'm kind of ambivalent about which convention I like more, but I decided to go with the 0. For the negative binomial, I definitely like the de Groot convention more. So if you look in Ross, he'll start the negative binomial at r, because he's counting the successes as well. So even if you're successful the first r times, then those would count. And we're starting it at 0. So it's very easy to convert back and forth between those. It's just you have to be careful, like if you just blindly copy a formula from somewhere and they're using a different convention, then it's going to be completely wrong. But as long as you're careful, then it's not really a big deal. Just to say a little bit more about that geometric thing, let's define what is sometimes called the first success distribution. Let's let x x be fs of p. That's first success of p. That is the time until first success. Again, we have these Bernoulli trials. And this one is counting the success. Just because I've noticed that sometimes students get confused about how to convert back and forth, and it should be very easy. So once you've thought about it a little bit, hopefully it'll be easy to do that. So if we just write geometric, we're not counting the success. If we write fs of p, then we're counting the success. That's first success. Okay? Well, if we wanted to deal with this problem, we don't need to go through like a whole new theory and everything. All we have to do is say, well, let's just if we wanted to deal with such an x, all we would do is just let y equal x minus 1, right? Then, by our definition, y is geometric p. I subtracted 1 just because I don't want to count the success, that's all, okay? And so then it's easy to relate the two PMFs, right? Because if we want to know the probability that x equals something, just rewrite that in terms of y. That's very easy. And if we want the expected value of x, the expected value of x, well, x is y plus 1, so it's just e of y plus 1. And by the way, it's fairly common to omit, I'll write the parentheses for now, but it's fairly common in the literature to omit the parentheses with expected value when there's no ambiguity. Expected value of y is q over p. So this is q over p plus 1, which we can simplify by getting a common denominator. P plus q is 1. So that's just 1 over p. So that's a pretty nice result, too. A very simple looking formula for the expected value of the first success time. And 1 over p, this is pretty intuitive when you think about it. Let's see what that says. Suppose that our probability of success is 1 in 10. Then it says on average it would take 10 trials to get the first success if you include that success. So that kind of makes sense, right? You succeed 1 in 10 times, it's going to take about 10 trials. So that's all it's saying. Okay, so that's just how you convert between those things. Okay, so that's the negative binomial distribution. And that only leaves one more famous discrete distribution that we'll need, and we'll save that for next time. First, I wanted to do a couple more examples with expectation. So here's another problem I really like. That is, this is a problem that came from the Putnam exam a few years ago. So for those of you who don't know, the Putnam is one of the hardest math competitions in the country. It's an extremely difficult math exam, and that's offered every year. And most years, the median score on the Putnam is a 0, because most people who take it can't solve any of the questions, so they get zeros. So it's a very hard exam, and here's a problem that came straight off the Putnam. I like this problem because it illustrates what we're doing, and we can solve this problem very easily with what we're doing. Okay, so here's the problem. The problem says you have a random permutation of the numbers integers from 1 to n. So in general, they don't have a lot of probability on the Putnam, but they do occasionally have probability, especially when it's actually counting. That is, you could use the naive definition of probability, although that would actually not be a good idea here. So by random, they mean that all permutations are equally likely. So there's n. So we take the numbers 1 through n and permute them in any order, all n factorial equally likely. And let's assume n is at least 2 to avoid some stupid cases. Now, I have to tell you what the question is. The question is, find the average or expected number of local maxima. So I have to tell you what a local maximum is. Expected number. So this was all defined on the problem. And this is exactly what the problem was. I'm just phrasing it in my own words, but this was exactly the problem. Find the expected number of local maxima. And it's easiest to explain what local maxima is just by making up an example. So I'll just permute some numbers. Let's say we had 3, 2, 1, 4, 7, 5, 6. Okay, so that's a permutation of 1 through 7. Local maxima is any number that's bigger than its neighbors, right? So 7, I'm going to circle the local maxima. 7 is bigger than 4 and 5, okay? Now, the 3 only has one neighbor, the 2, because that's at the end point. But 3 is bigger than 2, so that still counts. Okay, so there's two different types. Either you can have one that's in the middle somewhere, and then it has to be bigger than both its neighbors, or you could have one at the end, 6 is bigger than 5. So in this example, I mean, you can make up whatever example you want. In this example, it happened that both endpoints are local maxima, and one point in the middle was a local maximum, and none of these others are local maxima, right? Okay? Does everyone understand the problem now? So we want to know on average, that is, this is one of 7 factorial things I could have written down. We want to know on average how many local maxima are there. Okay? So actually, not only was that a Putnam problem, but I was kind of like looking around on some Putnam forums a couple years ago where people were discussing that year's Putnam. A lot of people who took the exam thought this was the hardest question on that year's exam. So now let's solve the problem. Okay, so first of all, we need some indicator random variables. So let's let ij be the indicator random variable for position j being a local maxima. So of position j, that is, this is position 1, 2, 3, and so on. Position j, either it does, right? That's an event. Either it does or it does not have a local maximum at that position, right? So that's what we're looking at. Position j having a local max. Okay, so that's a natural indicator random variable to look at. And of course, j goes from 1 to n. Now, the sum of these ij's is the number of local maxima, right? That's what we're trying to count. So what we're interested in is the expected value of I1 plus blah, blah, blah plus In. And by linearity, that's just E of I1 plus E of I2 plus E of In. Okay? Now, the only thing Well, the main thing we have to be careful about here is to split it into two different cases. One is that because we have these endpoints and we have these non-endpoints, right? So we do have symmetry in the sense that what was the probability that this number here, which happened to be a 7, was bigger than both its neighbors? Well, if you look at these three positions here, the 4, the 7, and the 5, by symmetry, they're equally likely to be in any of the 6 possible orders, right? And of those 6 orders, there's 2 ways that the biggest could be in the middle, right? Because it could have been 4, 7, 5 or 5, 7, 4. 2 over 6 is 1/3. Or an even better way to think of it is that we're looking at these 3 positions here, right? The largest number among those 3 is equally likely to be in any of those 3 positions, right? The 7 was equally likely to have been there, there, or there. So there's a 1/3 chance that the biggest number is in the middle. A common mistake with this would be to say it's 1/4, because there's a 50-50 chance that this number is bigger than this number, and there's a 50% chance that this number is bigger than this number, and so a lot of people would say 1/4 here. That's the same mistake as, you remember the problem about, what's the probability that A is older than B given that A is older than C? Similar type of problem. This being bigger than this is not independent of this being bigger than this, okay? And, well, we just showed that they're not. If they were independent, it would be 1/4. But I just argued in 2 different ways that it's 1/3, okay? So with 2 correct arguments, I got 1/3. And with 1 incorrect argument, I got 1/4. So I'm going to go with the 1/3. Now we can use symmetry, as long as we're careful to distinguish between the intermediate points and the endpoints. There are n-2 intermediate points. Each of them is 1/3 probability. That is, the expected value of remember the fundamental bridge. The expected value of an indicator is the probability of the event. The probability of the event is 1/3 for each of these intermediate coordinates. Lastly, we just have to look at these 2 endpoints. So there's 2 of them. And for those, it's just 1/2, because it was equally likely that this number is bigger than this number versus this number being bigger than this number. So for the endpoints, it's 1/2, because there's only 1 neighbor. So those are both 1/2. So it's just n-2 over 3 plus 1, which we could simplify a little bit, n plus 1 over 3. So it's basically, again, a one-line thing once you've set up the indicators and you understand your linearity and your symmetry. Let's just check, does this make sense in the extreme cases? Well, if n equals 1, that's a really stupid problem. You just have one number and it's a local maximum. So that's why I assumed n is at least 2. Now let's just quickly check what happens if n is 2. Well, then we either have 1, 2 or 2, 1, right? And either way, there's 1 maximum. And this says it's equal to 1. So, okay, so that worked. And let's see. Another nice thing, this grows linearly, and it goes to infinity as n goes to infinity. I guess it would be a little bit weird if the expected number of maxima did not go to infinity as n goes to infinity. So we can do a couple quick little checks like that. But anyway, that's the argument, okay? So it's those same tools we were talking about last time, just use those in combination. Indicators, linearity, symmetry, and you can solve some really hard problems. All right, so let's do one more famous example that does not involve indicator random variables, because I don't want you to think that's everything there is to expectation. So this one is called, this is called the St. Petersburg paradox. And we can debate whether it's really a paradox or not. Well, it's not a paradox, as I've said before. There's not any true paradoxes, but that's what it's traditionally called, and it is something that makes you think, which is why we're doing it. This is about thinking. So here's the problem. So someone offers you the following game. They're going to flip a fair coin over and over again until the coin lands heads for the first time. Okay? Now, if the coin lands heads on the first trial, you'll get $2. If it's the second trial, for the first outcome of heads, if it's the second trial, you get $4. If it's the third trial, you get $8. And if it's the fourth trial, you get $16, and it doubles every time, okay? So you get, let's say, 2 to the x dollars, where x is the number of flips of the coin until it lands heads. First H, including the H. So that's what we call the first success distribution. So it's a geometric distribution plus 1 because we're counting that success, including the success. And the question, so obviously if you're playing this game, you're hoping that the coin will land tails for a long time because this keeps doubling every time, and the longer it goes on, the better it double. It grows exponentially fast, like if x is 10, then you'll get $1,024, and so on. It keeps doubling, okay? So the question is, how much should you be willing to pay to play this game? Now, some people, have moral or other objections to gambling or are very risk averse and whatever, and some people are gambling addicts and so on. But let's assume, let's define fair. The standard definition of a fair game would be what value, obviously you should pay something to play this game because you're going to get some money out. What value would make what price would make the expected value 0? Okay, that would often be called the fair price.